after all that introduction, I guess I have to produce a little more. I'm so deeply honored by the support, and I want to express my profound thanks to the Cognitive Science Society and the Selection Committee, Bob Blushko and the Blushko-Samuelson Foundation, and the folks who took part in the symposium this morning. If you were here, a lot of what I'll have to say will be familiar. If you weren't, maybe it will be anyway, I hope. I seem to be the first theoretical linguist to have received this award, so I feel sort of privileged to be able to talk about how the kind of work I do, which might seem a bit old-fashioned, nevertheless how it can and should play a role in cognitive science at large. My deepest concern over all these years has been with a set of basic questions behind the computational theory of mind. Namely, what is the repertoire of patterns that an organism can encode, and how does it acquire this repertoire? How do perceivers or learners internally represent the input, and how do they represent their hypotheses so that they can compare them with the input? In other words, what are the different kinds of mental representations in terms of which an organism encodes its understanding of the world and formulates its actions? Unfortunately, I think over the years the term mental representation has become sort of an empty code word for something like whatever information the brain uses. And I want to go back to the roots of cognitive science and ask for a thorough and formal characterization of mental representations, including representations of the rules that define or license generalizations. Now, in linguistics, this is what linguistic theory is really about. The grammar of a language is supposed to delineate the repertoire of phonological and syntactic and semantic structures in terms of which a speaker can construct utterances and discourses in comprehension and production. In vision, this is what David Marr called a computational theory, and he formulated an elaborate theory of three kinds of representations that are involved in recognizing objects and the connection between them. Since Marr's death, I think there have been other theories around, but those that I've encountered at least really fail to scale up to the full complexity of the problem, at least as the way he aspired to. For another case, Fred Laerdal and I developed a detailed theory of the representations involved in music. What does that mean? Structures that listeners construct that make music more than just a sequence of notes, and the principles that listeners use to construct these structures. And in yet another domain, my former student Neil Cohn has developed a theory of narrative structure that applies equally to linguistic and visual narratives. Now, I think other domains of cognitive science call for the same approach. If you're studying episodic memory, I'd like to know what counts as an episode. How is it encoded? What are the units from which encoded episodes are constructed? How are they composed? For instance, something simple, how do I code my memory of where I parked my car this morning, or what transpired at the department meeting? If you're studying embodied cognition, I'd like to know how our experience, and especially our bodies, are encoded by our brains. And I'd also like to know how the brain encodes all the other things that are supposed to be understood with reference to the body, and how these encodings reflect this metaphysical leap from concrete body experience to other kinds of cognition, such as like moral thought. If you believe in item-based or exemplar-based learning, if you think learning consists of encoding all the instances of whatever you've experienced in some domain, and that understanding novel inputs is just a matter of interpolating among instances, I'd like to know exactly how to encode instances and what are the dimensions available for encoding them. And I'd like you to agree that those dimensions, in terms of which experience can be encoded, can't themselves be learned because they form the basis of learning. So they somehow have to be there in advance in order to encode experience at all. If you believe in statistical or probabilistic learning, I'd like to know the repertoire of forms over which you're running your statistics. If you believe in predictive or hypothesis-based perception, I'd like to know the terms in which predictions and hypotheses are encoded, and the terms in which evidence for hypotheses is encoded. And if you believe in Bayesian perception or learning, I'd like to know how the priors are encoded. Now, I recognize that there's something right about all these approaches I mentioned. We do code episodes. We do base abstract reasoning on principles of physical experience. We do learn on the basis of instances, of course. And we do have stochastic and probabilistic factors involved in our perception and behavior. But I think something important is missing from these approaches, to the extent, of course, that I'm familiar with the literature, which is, not that great, probably. But I don't see an explicit and sufficient general theory of the mental structures that are being computed and learned. Now, I want to stress that I don't want a theory of structure to live in a vacuum. Like David Marr, and unlike Chomsky, I want the formal theory of mental structures to embed gracefully in a theory of how moment-to-moment processing takes place and how learning takes place. My working hypothesis is that memory and processing and attention and learning are pretty much the same all over the brain. And I believe that structural features like grouping and sequencing and even recursion are common to many different kinds of mental representations. But then you have to say what makes vision different from language, and what makes language different from music, and music different from actions like washing dishes, and washing dishes different from morality. And my working hypothesis here is that these differences are a consequence of the character of the mental structures that are appropriate to each one. And whatever similarities these domains share are sort of like the similarities we find in cell structure and metabolism across muscle cells and stomach cells and neurons. But we can't test this hypothesis without having some details about what these different mental structures are like. It's also incumbent on a proper theory to say how the various forms of mental structure interact with each other to produce our capabilities of understanding and behavior. For instance, we managed to talk about what we see. And this means that the mental structures responsible for visual cognition somehow have to interact with those responsible for language. These faculties can't be completely encapsulated from each other in Fodor's sense. So a theory of any faculty has to show how it makes contact with other faculties. And beyond that, of course, I hope we'd all like the accounts of processing and learning eventually to be describable in terms of neural computation, and that's pretty demanding. As far as I know, we don't have the faintest idea of how neurons encode something as simple as a syllable, say bat, not to mention the meaning of a sentence. We may have some idea where in the brain speech sounds are encoded or where they're marshaled into words, but I don't think we have any idea how. Now, of course, not every theory is a good theory. Take mainstream linguistic theory, for instance. On one hand, it's been terrific at leading to fruitful exploration of a huge number of linguistic phenomena in a huge number of languages. But on the other hand, it hasn't fit very well with theories of processing and acquisition, and that's led many researchers, though not all by any means, to give up trying to use it to guide experimental work. What's more, mainstream linguistic theory has not been internally coherent. A typical grad student in linguistics these days learns phonology in terms of optimality theory, syntax in terms of the minimalist program, or maybe if they're lucky, HPSG, and semantics in terms of possible worlds. And none of these has any connection to the others. And for the most part, this disconnect is true of the theoretical literature as well. Can this be the right overall theory of language? To me, it's like a beast with the head of a cat, the wings of an eagle, and feet from elephants and crocodiles and various other parts. The pieces don't fit together at all, much less relate to the mind in the way that generative grammar originally aspired to. Well, over the past 20 years, I've been trying to develop a better integrated theory of language called the parallel architecture. And the goal of this is to retain the insights of all the constituent parts, but find a way to fit them all together. And I developed these in most detail in my book, Foundations of Language, and the book I wrote with Peter Kulikover, Simpler Syntax. Unlike standard generative grammar, which includes, it includes a well-worked out theory of meaning called conceptual semantics, which I've tried to ground in psychological research on non-linguistic cognition, both spatial cognition and social cognition, including morality. At the same time, simpler syntax addresses all the traditional concerns of generative syntax, in an approach that's much more surfacey than standard generative grammar has ever been. In particular, there's no movement and almost no empty nodes. So it's far more constrained than standard accounts of syntax. And in this respect, it has a lot in common with frameworks like HPSG, cognitive grammar, and construction grammar. Now, what makes me think this approach is on the right track is that it's opened up all sorts of interesting avenues for research. And today I'd like to run through some of them. So the first one is the architecture of the grammar. I want to take Chomsky's term, knowledge of language, actually more literally than he does, very psycholinguistically. Knowledge implies there's something stored in memory. So in these terms, the major questions of generative grammar come out like this. First, what linguistic units and linguistic complexes do speakers of a particular language store in long-term memory? And the standard answer is the lexicon. Second, what procedures do speakers use to construct novel composite structures, in particular to relate meaning to sound or, in the case of sign languages, to gestures? And the standard answer is the grammar. Third, what procedures do language learners use to construct the first two kinds of knowledge? And the standard answer is universal grammar, or the language acquisition device. And the biggest dispute, I think, in linguistics over the years has been what aspects of these procedures are domain-specific and what aspects are domain-general. Now, I think any mentalist theory of language has to face these questions, and here I'm 100% in agreement with standard generative grammar. But from this point, the theories start to diverge immediately, and the first difference is in the overall architecture. The received view is that the combinatorial structure of language arises in syntax, and that the combinatorial structures of phonology and semantics are derived from syntax. But already in the 1970s, phonologists showed that phonology has its own independent combinatorial principles. And in practically every theory of semantics on the market, meaning has its own primitives and principles of combination, independent of syntactic structure. Now, mainstream linguistics, I think, has mostly ignored the combinatorial independence of phonology and semantics from syntax. But if we take it seriously, we arrive at a parallel architecture in which phonology and syntax and semantics are on an equal footing. So each of the structures here has its own combinatorial principles, but in addition, they have to be linked by interface principles, because that's what enables language to map between sound and meaning. So a phrase or sentence is a triple of well-formed phonological, syntactic, and conceptual structures with well-formed links through the interface components. Why should we think about language this way? Well, one important reason, sort of a top-down reason, is that it allows us to situate the language faculty nicely within the rest of the line. So let me return for a minute to the question of how do we talk about C. And my hypothesis, inspired by Marr's work, is that conceptual structure is connected by another interface to another form of mental representation that I call spatial structure. This encodes your understanding of the geometrical configuration of the physical environment, and it's connected to systems of perception as well as to the generation of action. You can't derive spatial structure from syntax. Here's how I think it fits in. Spatial structure gets its inputs from vision, from haptic perception, the sense of touch, proprioception, the sense of one's body position, and none of these can be derived from the others. Now, the parallel architecture is perfectly natural with this view of things, because its independent representations, coordinated by interfaces, are consonant with what pretty much has to be the case in the rest of the mind. And this layout makes it easy to plug in further domains of linguistic structure. For instance, orthography has its own internal principles, plus an interface to the visual system, so you can see what's written, plus an interface to phonology or morphology, so it represents words. And sign language has, instead of normal phonology, a phonology of structured gesture with interfaces to vision and motor system. And sociolinguistic variables like formal versus casual speech register can be modeled as an interface between perceptions of social situation and the use of particular words or expressions as appropriate to that social situation. So the parallel architecture gives us the flexibility to connect up new domains of cognition as the need arises. Next, I want to turn to a second major difference between the parallel architecture and the standard generative grammar. It's traditional to distinguish the lexicon, the list of words, from the grammar, the rules. And from the very beginning, generative linguistics adopted this view. The lexicon was encoded declaratively, and the rules of grammar were viewed as procedures for constructing sentences step by step. Now, of course, the rules of grammar, like the words, have to be stored somehow in memory. So we might want to say the lexicon and the grammar are stored differently in the brain, whatever that might be. Michael Ullman has been pushing this view. Well, I want to show you that there's actually a lot to be gained by giving up this assumption. The argument goes by sort of a slippery slope. There are things in the lexicon that are progressively more and more rule-like, so there seems less and less reason to distinguish them from things that everyone considers to be rules. And when you reach the bottom of the slippery slope, you find it's not so bad down there after all. And there are versions of this argument in HPSG, cognitive grammar, and construction grammar, as well as in my work. So how do we start? We start with what's a word? Well, in anybody's theory, a word is an association of a piece of phonology, a piece of composite semantics, and some syntactic features stored in long-term memory. Well, this is the stereotypical case, but now think about words like hello and ouch. They have phonology and they have semantics, but they have no detectable syntax. They can occur alone as full utterances, just like that. But they occur in combination only in things like hello, Bill, which doesn't have much structure, and in quotative context like hello, she said, where you can insert anything at all, even an expression of another language. English also has a few words that have phonological and syntactic features, but no semantic features. They're just functioning as grammatical glue. For instance, the epenthetic it, and it's noisy in here, and the other items in red on the screen. And then there are nonsense words like hey diddle diddle. These have nice legal phonology, but they have no syntax or semantics. Their linguistic function is just to fill up metrical space in poetry or songs. And if you know the song, you recognize these the very same way you recognize words. So lexical items can have all different combinations of phonological, syntactic, and semantic features. That's not so easy to say in standard architecture, but in the parallel architecture, it's just one little adjustment you have to make to loosen things up. Well, okay, what else do you have to store in your lexicon? Well, for one thing, you obviously have to store idioms and other fixed expressions in some form or another. For instance, kick the bucket has a phonological structure, it has a semantic structure approximately equivalent to die, and it has the syntactic structure of a verb phrase. And we know it's a verb phrase because kick gets inflections just like an ordinary verb. So we learn from this that lexical items can have an internal syntactic structure that has to be stored. Now, in addition, idioms can have argument structures, so things like take for granted and these other items require a direct object just like ordinary transitive verbs. And by the way, they're discontinuous, so the lexicon must allow us that. There's another class of idioms that I call constructional idioms. They use normal syntax, but to unusual semantic ends. So look at the first example here. Bill belched his way out of the restaurant. Now, syntactically, it has a typical verb phrase, but the verb belch doesn't usually allow a direct object, but here we have this weird thing, his way, in direct object position. Belch also doesn't allow a path expression like out of the restaurant. And even though there's no verb of motion, the meaning of the sentence, in fact, involves Bill going out of the restaurant. So what's Belch doing in there? It's describing the manner in which he goes out of the restaurant or something that he's doing concurrently. So there's this non-canonical mapping between syntax and semantics marked by the phrase his way in object position. And it's kind of productive. You can use any old verb of the right semantic type here. You can drink your way across the country or knit your way through a conference. The other two constructions on the screen are other mappings of this sort with different semantics, marked by a way in the first one and head or other body part off in the second one. And knowing these constructions is part of knowing English. For each one, you have to store its syntactic structure. You have to store how it links the syntax to semantics in other than the normal way. plus the phonology of the designated elements way, away, or head off to signal that something unusual is going on. Now, there are other constructions, like these four, that don't have any distinguishing phonological content, so they're getting to be even more like rules than words. So the bus rumbled around the corner means that the bus went around the corner, making rumbling sounds, even though there's no verb of motion. In that travesty of a theory, the syntactic head is travesty, and theory is a modifier, but semantically it's the other way around. The expression refers to a theory, and travesty is a modifier. In the light verb construction, the direct object, a hug, provides the semantic content that's usually expressed by a verb, and the verb is more or less a dummy that provides argument positions. And finally, in the paratactic conditionals, there's no if-then, but the meaning is perfectly clear. This is an example from conversation last week. Again, you have to learn and store these rule-like constructional idioms as associations between a syntactic complex and a semantic complex. But the basic formalism is the same as for words, except the syntax is composite, not just a couple of features. And in this last group, there happens to be no phonology. So people in construction grammar have written about lots of things like these, as Ann Polkover and I have as well. The language turns out to be full of them once you think to look, but people didn't think to look until the late 1980s, right? Adele was sort of the co-discoverer of this one construction with me. Now, mainstream grammar largely ignores all these phenomena, and when it encounters them, it struggles because it assumes that there's a one-to-one relation between meaning and some covert level of syntax. But within the parallel architecture and construction grammar, they emerge as variations on a theme. They're stored pieces of syntactic and semantic structure, sometimes with accompanying phonology, sometimes not. But now look what happens. Using the very same formalism, we can state a language's phrase structure rules as syntactic schemas without any association to phonology or semantics. So here's a partial rule for the transit of verb phrase in English. Mike Tomasello calls this a slot and frame schema. Jana Fodor calls it a treelet. This is also sort of the basic unit in tree-adjoining grammar. I don't care which notation you want, but given what we've seen so far, we can think of this as a lexical item too. After all, we have lexical items with just phonology, like fiddle-dee-dee, items with just phonology and syntax, like the do of do support, items with just phonology and semantics, like hello, idioms and meaningful constructions with lots of syntactic structure. So this happens to be an item with only syntactic structure. It's just another logical possibility in the system. So at this point, we've gotten to the bottom of the slippery slope from words to rules, and it actually makes some things work better. For one thing, we can easily incorporate these intermediate cases like idioms and constructional idioms, where standard approaches are more or less at a loss. This leads to the hypothesis that many, maybe all phenomena that we previously called rules of grammar can be formulated as pieces of structure stored in the lexicon. In order to bring this off, we have to formulate syntax in terms of declarative licensing conditions, as in HPSG, LFG, and construction grammar, rather than in terms of the step-by-step derivations of the standard generative approach. So we have to get rid of the very seductive procedural notion of movement, such as the idea of moving a WH word from some underlying position to the front of a sentence. So how does a theory like this deal with all these things like passive and raising and long-distance dependencies, which always seem very natural in terms of movement? Well, all of these different theories, HPSG, LFG, tree-adjoining grammar, and simpler syntax, and various other frameworks, all attempt to work this out, and I think with a good deal of success. I'm not going to go through the arguments here. But a big part of my current work is directed toward extending this hypothesis to morphology and phonology. This turns out to be a substantial challenge, but I am trying to put my money where my mouth is. Assuming that it works, the upshot is that the lexicon includes both the words and the rules. From the perspective of standard generative grammar, this looks kind of weird, but it has a lot of interesting payoffs. For instance, as in construction grammar, we can now think of learning a rule as adding a schema to the lexicon that's based on generalizing over existing items. This schema then forms an inheritance hierarchy with its known instances. And this is formally more natural than creating a rule in an entirely different format, as is required by the traditional declarative procedural divide. Another payoff that I want to talk about at a little greater length is in thinking about language processing. First, let's go back to what a word is. It's a long-term memory linking of pieces of phonological, syntactic, and conceptual structures. In the parallel architecture, you can think of a word as a little interface rule. It tells you that if you encounter this piece of phonology, say cat, you can create a link to this piece of syntax, noun, and this piece of conceptual structure, feline, pet, whatever it might be. And this gives us a nice way to think about lexical access in sentence comprehension. Suppose phonetic perception creates some phonological string, say cat, in working memory. Then the processor sends a call to the lexicon. Do any of you guys in there sound like this? Cat. And various lexical entries raise their hands. They're activated as candidates for what you're hearing. But once their phonology is activated, they also bring along with them their syntax and semantics, which then can come into play in attempting to construct an interpretation for what you're hearing. Similarly, in production, we build some intended message, a conceptual structure in working memory, and the processor calls the lexicon. Do any of you guys in there mean this? And various entries raise their hands. And once their meanings are activated, they drag along their syntax and phonology, and that gives the processor something to use in constructing the form of what we're going to say. Now, this corresponds pretty well to the way a lot of people think about lexical access these days. Different approaches have different bells and whistles. But what's nice is that it fits so comfortably within the parallel architecture's approach to the lexicon and the composition of linguistic structure. So let's see how this extends to parsing. Again, the parallel architecture's way of describing tree structures is to list available pieces of structure or treelets like these. As in tree adjoining grammar, you build a tree by clipping together these nodes, these treelets at nodes that they share, working from the bottom up or the top down or from anywhere in the middle, as long as the resulting tree ends up with S at the top and terminal symbols at the bottom. So the process of combining treelets is compatible with left to right and top down or bottom up computation. So suppose an utterance begins with the phonology the. This will activate the lexical item the, which puts a determiner node into play in syntax, giving us this subtree. Determiner calls the lexicon, what structures can I fit into? And noun phrase answers, I have a determiner, so the noun phrase treelet activates and clips on to produce this. In turn, if it's an initial noun phrase, it calls the lexicon, who can I fit into? And one of the treelets that answers is S, which gets clipped on giving this. And then the verb phrase calls the lexicon, giving a verb node like this. And we're on our way to anticipatory parsing, that is, setting up grammatical expectations on the basis of an initial word. And subsequent words in the sentence can then be clipped into the tree on the basis of this top-down structure. But things might go in a different direction from this initial prediction. Remember, we just have the noise the. The sentence could be something like, the more I read, the less I understand. Well, here, the isn't a determiner, it's a mark of a special construction called the correlative conditional. This construction has to be stored as a schema in the lexicon alongside the other constructional idioms that I mentioned before. How does this sentence get parsed? I think the simplest hypothesis is that the also recruits the correlative conditional schema right along with the determiner and noun phrase schema, though at a much lower level of activation thanks to its much lower frequency. But suppose the next word happens to be more. Then the correlative conditional gets a bit happier and clamors for more attention. It's more confirmed by what's found in the input. But it better not turn off the noun phrase schema altogether, because the sentence could turn out to be something like, the more attractive theory doesn't win, which is a standard noun phrase. So these two constructions have to be in competition for some distance down the line until you can resolve the choice. Well, this gives us a nice way to think about garden pathing and the like. We can ask things like, what are the relative probabilities of different competing analyses? How long are alternative analyses maintained? And again, these are stock and trade questions in the parsing literature, but they emerge very cleanly from the perspective of the parallel architecture. Now, I slipped in something here that I want to say a little more about. The idea that the noun phrase schema is more highly activated than the correlative conditional schema on account of its higher frequency. And of course, we know that's what happens with words. Frequency matters for access time. But I've now extended it to syntactic structures. In a standard generative grammar, it would be hard to make this connection. But again, in the parallel architecture, where syntactic treelets and constructional idioms are right in there in the lexicon with words, this is a perfectly natural conclusion. More frequent syntactic schema should be easier to access than less frequent ones. It also gives us a natural account of syntactic priming, where, say, hearing a ditransitive sentence like he gave Bill the ball increases the probability of producing another ditransitive rather than a prepositional dative like she sent the package to Harry. Nowadays, we take syntactic priming pretty much for granted, but in Kate Bach's original work on syntactic priming, she noticed that this is kind of unexpected. Words prime, presumably from a transient increase in activation potential. But she asked, why should there be priming on the application of phrase structure rules of all things? Well, in the parallel architecture, the ditransitive construction and the prepositional dative configuration are alternative treelets in the lexicon, so just as word is prime, so do phrase structure configuration. Well, again, this analysis is sort of common sense, but the architecture lets us make a direct connection between the structures that are posited by the theory and their behavior and performance. So, for example, the theory identifies situations where syntax doesn't map to semantics in canonical fashion. We talked about some of them. So it might predict that non-canonical mapping should lead to complexity in processing, revival of the derivational theory of complexity, horrors. But we ought to be able to detect this complexity experimentally. And in fact, a number of these situations have been investigated, and I'll just mention one, the light verb construction, which I mentioned earlier. So take a light verb sentence like Judy gave Henry a hug. It's pretty much synonymous with Judy hugged Henry. The noun hug signifies an action, which would be normally denoted by a verb, and meanwhile the verb functions as sort of a placeholder. Because of this mismatch between syntax and semantics, the parallel architecture predicts that processing ought to require some extra work, namely identifying Judy and Henry as the agent and patient of the predicate expressed by the noun hug. And students and colleagues of mine have detected this extra processing in a variety of experiments. So, in a cross-modal lexical decision task, Maria Pinyango and Jennifer Mack found an extra processing load 300 milliseconds after the presentation of the object of the construction, in a time frame that's believed to be associated with semantic rather than syntactic processing. Eva Wittenberg and Maria Pinyango replicated this finding in German, where you could make the critical point that clause final verb. And they found this extra strain on processing, despite the fact that the verbs in question were more frequent as light verbs than they were in non-light constructions. So just the opposite of what you might expect on the basis of frequency. Eva, along with Gina Cooperberg, Martin Paczynski, and Heike Wiese, reported ERPs in German light verb constructions, and they found widely distributed, frontally focused, sustained negativity, 500 to 900 milliseconds after presentation of the critical word. So this response was quite different from the response to anomalous and ungrammatical sentences, and they attributed it to this extra processing that's required to align the thematic roles. Finally, conventional generative grammar has to argue that a light verb construction like give someone a hug has a different syntax from an ordinary verb phrase like give someone a book. Eva and Jesse Snedeker tested this prediction by running a syntactic priming experiment. They showed that non-light verb double object constructions like give someone a book can be primed by light double object constructions like give someone a hug, just as well as by another non-light. So this is evidence that syntactic structure is the same in the two as the parallel architecture claims. In other words, the theoretical analysis of the parallel architecture has brought to attention a phenomenon that previously had received little experimental investigation, actually little theoretical investigation too. And the results bear out the parallel architecture's account over theoretical alternatives. Where do we go from here? Well, a challenge I find myself facing is how to reinterpret the vast experimental literature on language processing in these terms. In particular, how can lexical access be formulated to include treelets and constructions? To what extent are multiple structures kept in competition? What facilitates what inhibits what? It's bewildering. This is a project that I'm actively at work on at the moment. A final issue I want to talk about tonight is languages that don't have much syntax. So let's start by thinking about the interfaces in the parallel architecture. I diagrammed the architecture like this, with one interface between phonology and syntax, and one between syntax and semantics. But could there be another interface, a direct route between phonology and semantics that bypasses syntax? This would be impossible in a traditional generative grammar because there everything comes from syntax. But it's a natural question we can ask in the parallel architecture. Well, we've already seen one sort of linking like this, words like hello and ouch that only have phonology and meaning, but no syntactic properties. And this is also an attractive way of thinking about the effect of contrastive stress on topic and focus. So the difference between Joe likes ice cream, Joe likes ice cream, Joe likes ice cream, where the only thing that overtly signals the meaning difference is phonology. But we can ask a deeper question. What would happen if we took the parallel architecture and erased the syntactic component? Bye-bye. So there would be only a connection between phonology and semantics. What would be a language? What would a language be like that was structured like this? Well, it could still have words that correlated pieces of sound with pieces of meaning, but words couldn't have parts of speech. Words could only be distinguished by whether they denote objects, actions, or properties. That is, by semantic features. A language like this could still have sequences of words in linear order, and it could have prosodic structure, that is, constituents that are delimited by intonation contours. But it couldn't have noun phrases, because it doesn't have nouns, and it couldn't have verb phrases, it couldn't have subjects, it couldn't have objects, and it couldn't have clauses. That means it couldn't have subordinate clauses, so syntactic recursion would be absent, although semantic recursion might still be there. A language like this would still be able to assign semantic roles in terms of the linear order of words, which are present in phonology. Principles like agent precedes patient, focus last, or modifier follows what it modifies. Words might have internal morphological structure, but this would have to be based on semantic rather than syntactic grounds. So I'll call a grammar with these properties a linear grammar. Now, this is just a theoretical fantasy. No. There are, in fact, languages that have these sorts of properties. So David Gill has written extensively about Riau Indonesian. This is a language spoken by several million people in an urban environment, so it's no real exotic thing. And he presents a persuasive case that this language has no parts of speech, almost no function words, virtually no morphology, and at least on my analysis in terms of parallel architecture, virtually no syntactic structure and definitely no recursion. The word order is determined entirely by semantics, and interpretation typically requires a great deal of pragmatics and contextual support. My reading of the literature on pigeons suggests that they're structured this way as well, with, if anything, a greater degree of variability and necessity for pragmatic support. But they still have phonology and semantics. There are more examples coming from emerging sign languages like Nicaraguan Sign Language, Abu Said Bedouin Sign Language, and a village sign language from Turkey called Central Taurus Sign Language that's newly discovered, and it's currently being investigated by my students, Rabia Ergin and Naomi Perloff-Caselli. Particularly at the earlier stages of these languages, there's no evidence for syntactic structure, though morphology does develop relatively early. Again, there's semantically based principles of word order, there are no function words, there's little or no evidence of embedding or even constituent structure beyond that provided by prosody, and there's a great reliance on pragmatics. And we also find these properties in home signs, that is, the signing systems invented by deaf children who have no sign input. Finally, Wolfgang Klein and Clive Perdue have argued that late second language learners in naturalistic environments invariably pass through a stage that they call the basic variety, which also corresponds pretty closely with the characteristics of linear grammar. In addition, looking from this perspective, I found subsystems of English that have these sorts of properties. And the clearest case is compounding, where you simply jam two words together and stipulate that normally the second one in linear order is the semantic head. So beef stew is a kind of stew, but stew beef is a kind of beef. Beyond that, the proper interpretation is largely a matter of pragmatics, as you can see from these examples. Coming back to processing, I've begun to think that principles of linear grammar are at work in normal sentence processing too. They seem to correspond rather nicely to things that people have called perceptual strategies or good enough parsing, and that show up in garden pathing and other measures of parsing difficulty. A lot of people say, well, this is just general purpose cognition, but they're still mappings of phonology to semantics. That is, their language, just language without syntax. In the simplest cases, they reinforce syntactic analysis, but in cases like reversible passives and object relatives, they conflict with the syntactic analysis. So in those kinds of constructions, the agent doesn't come first, and this might help account for their difficulty. Verifying this conjecture is going to, again, take a thorough review of the parsing literature, and I've begun to undertake it, but I can't give you any strong results yet. Meanwhile, there's a lesson here. There are schools of thought in linguistics, and especially outside linguistics and cognitive science, that question the need for syntax in natural languages. I think this investigation of linear grammar gives us a benchmark for what languages without syntax can be like. There are no function words, no inflectional morphology, no passive, no subordinate clauses, and a huge reliance on pragmatics. To me, at least, it shows how essential syntax is to expressiveness in developed languages, while at the same time we can acknowledge that there are circumstances where you can do without it. This raises, of course, all sorts of interesting issues about language acquisition, innateness, critical periods, the evolution of the language faculty, that I don't have time to go into here. Well, okay, to sum up, the parallel architecture grounds linguistic theory in the questions, what do you store and in what form? And how do you assemble these stored pieces into utterances? And the answer, I think, turns out to be rather surprising from the point of view of mainstream linguistics. Words and rules and all sorts of intermediate phenomena are stored in a common declarative format, namely as pieces of phonological, syntactic, and conceptual structures linked by interface principles. And the pieces are not assembled through a step-by-step bottom-up or top-down derivation, but rather by this operation of opportunistically clipping pieces together, which we can directly instantiate in a rather natural model of processing. Of course, many parts of this story, as I've said, are found in other approaches to linguistic theory and language processing. I think what's new is the synthesis of these insights into a coherent story that offers a better chance for integration of linguistic theory with psycholinguistics and cognitive science at large. My measure of success is when you get the theory right, all kinds of interesting prospects for research open up, both theoretical and experimental, and I'm trying to give you the flavor of that. So I want to conclude by going back to my challenges for the field of cognitive science as a whole. I hope it's not just up to me to develop theories of all the mental representations involved in human cognition. Life is way too short. But I hope that this talk might give a nudge to some of you, especially the younger folks, to take questions of representation more seriously in domains that you know about, and to recognize the potential that theoretical work of this sort has for stimulating more comprehensive and ecologically plausible experimental and modeling research. So finally, again, I want to express my deep gratitude to the Cognitive Science Society and to Bob Bushko for this great honor, and I hope I can live up to the challenge it presents. Thank you very much.